Hi guys, Tim's back again. I hope you can see me. I've adjusted things slightly, so I hope you can see things a little bit better. Apologies if it's not perfect. Right, what am I doing today? I'm going a little bit stir crazy, I think, what with one thing and another. But anyway, it's going okay. It's going okay. Make sure that the stuff I email you, the packs I ask you to do, that you do them. You learn how to do the stuff. Okay, you complete the packs and you self-mark the packs based on the mark schemes that I'm sending you and the information I'm giving you in these videos. Okay, obviously for AS students, you need to make sure you learn all this work and learn it properly, and I don't see why not, as long as I go through it carefully with you. Now, this video I'm going to finish off haloalkanes. So this is a summary video of haloalkanes, going through things, making sure you understand a couple of last things. I'm going to do the ozone layer, which is, I have already done this, but the video doesn't seem, it seems to be corrupted, so I can't upload it, I'm afraid. So I'm going to do another one on the ozone layer, which is the last bit of the haloalkanes. So far with the haloalkanes, there's about 3 things that we need to know. Overview of haloalkanes and nucleophilic substitution. Okay, in other words, an OH attacking the haloalkane and going in the other direction. The rate of hydrolysis when you take your haloalkane and you have a chloro, a bromo or an iodo, and you look to see which one reacts the fastest. The iodo one will be the fastest because it has the lower bond enthalpy. I've covered all that. So that's the second thing, the rates of hydrolysis experiment that you need to think about. And number 3 is the ozone layer aspects of the rate of hydrolysis, and making sure that the pack that I give you, which I'll show you shortly, we focus on some of the questions in the pack, make sure that we can do the questions in the pack properly. I'll try and make sure you can see the pack, but you'll get it emailed anyway, so you'll have no problem. That's to cover the, you know, the tricky little bits that maybe we haven't looked at before. That's the purpose of doing that. So without further ado, I think I'm going to teach you about the ozone layer and the role of haloalkanes in the ozone layer. Okay, and actually there is a question in this pack, for this is the pack I'm referring to. I hope you can see it. The pack is Haloalkanes 3. This is the mark scheme version, and I think I've sent you the pack with nothing on it, but it's hopefully anyway. Either way, make sure you understand I've answered these questions. And there is a question on the ozone layer which I will use to frame my explanation of the ozone layer. I'll show you that shortly. Okay, so have a look at that pack. Get that pack in front of you while I'm talking about it. Right, so the ozone layer, actually, if you look through this pack, you will find there's a question. Let's just have a quick look at it. Oh dear. That I'm going to talk about. First question. That one, I'm doing it up there. That one you should be able to do. We'll discuss it later, but you should be able to do it. 2, 3. That one talks about CFCs, dead easy. Okay, and this one, bit of a mess, is the ozone layer. There, 6 marks, 5 marks to be precise. This is what I'm going to teach you about the ozone layer, and hopefully I'll devise a way, if I can, to go through the packs a bit more carefully, but I shouldn't need to. Okay, they should be fairly self-explanatory. Right, so the ozone layer quickly. Let's go. So, haloalkanes. The role of CFCs the ozone layer. Okay? Right, role of CFCs. CFCs are chloro, fluoro, carbons. Okay? Developed, particularly used, have specific properties. They are very inert, unreactive. I know I've discussed this before, but there's bound to be a bit of repetition here. They're very inert, unreactive. Let me just check it. You can see stuff on the screen. It's all right. I'll just try and keep out of the way. That's the main thing. They're inert, unreactive. They're gases at room temp. Non-toxic. Okay. Now, that leads to their use as propellants in aerosols and refrigeration gases. It's been very difficult to replace them in these two roles. When you use an aerosol, okay, you've got a can with the stuff in that you need to spray on yourself, sure, hairspray, paint, whatever it may be. But the can is full of a propellant that's under pressure, so that when you press the button, the propellant propels, carries out the chemical that you want to use, you know, the paint or whatever it may be. So it carries out, say, the hairspray, the paint from the aerosol into the atmosphere. It just propels it out. Now, you need a gas that, if it's a propellant, not to react with the paint, with the hairspray, with whatever, the chemicals that's in the can. There's not many chemicals that are that unreactive that they can stay in a can as a propellant and won't mix or react with the stuff that's in the can. Okay, so chlorofluorocarbons can do that. Okay, that's their inertness helps them a great deal with that. Okay. Also, because they are gases at room temperature, they can be compressed. You press the top of the can, out they come. They're released. They vaporize in atmospheric pressure, an important quality. And of course, they're non-toxic. So those three things allow them to be used as propellants. Refrigeration gases, now I'm no expert on how fridges work, but they work by I think it's the evaporation condensation of a gas. In the back of your fridge, there's loads of pipes full of CFCs, and those CFCs, I mean, this is a bit dodgy, okay, but those CFCs in the back make the fridge work. And you don't want you want them to be inert, so that they're safe. If you puncture the back of the fridge or they escape into the atmosphere, that's absolutely fine. Okay, so CFCs are used in that role as well. However, there is an issue, because every time you use a container containing CFCs, you wouldn't even know. They don't smell, they're non-toxic. You don't even know what's happening. But every time somebody sprays, right, okay, in a can, out it comes into the atmosphere and it floats up into the upper atmosphere. And for years we ignored this. However, what we've discovered is that CFCs damage the ozone layer, which is gradually being repaired, I believe, as CFCs are being replaced. But you do need to know how the ozone layer is maintained and how CFCs damage that ozone layer. So I'm going to give you a sequence which exactly answers one of the questions in the haloalkanes back. Okay, right, so here we are. We'll keep that title there, haloalkanes, so you know what's going on. There you are. Okay. Right then. So, ozone absorbs harmful UV radiation. So we have an ozone layer that stops, that absorbs harmful UV radiation from the sun. Sure, some UV gets through, that's absolutely great, but some of it doesn't, and we need to be aware of that. Excuse me, I'll just check. Don't know really. Okay, so absorbs harmful UV radiation. That's what the ozone layer does, stops it coming through and harming us. Okay, that's great. And it exists up there in an equilibrium situation, okay, where ozone is O3 and it's continually in equilibrium in the atmosphere, upper atmosphere, with oxygen, O2, and an oxygen atom, O. Right, now that equilibrium means, according to Le Chatelier's principle, if that maintains the concentration. That is a specific question that gets asked. How? So I'll answer that. How is the concentration of the ozone in the atmosphere maintained? Answer: if the ozone concentration increases, the equilibrium will shift to the right-hand side to decrease the ozone concentration, increasing the oxygen concentration. If the oxygen concentration increases, the equilibrium will shift to the left-hand side, increasing the ozone concentration. So that's the first question answered, how that equilibrium maintains the relative amounts of ozone and oxygen in the atmosphere. So maintaining equilibrium, box ticked. Okay. Now, what happens? Well, in the upper atmosphere, we've seen this before, you might have some chlorine, right? And UV will come, as we have seen, all right, break that bond, and you get chlorine free radicals, which will damage the ozone layer. We'll discuss that shortly. But CFCs also have chlorine in them, so you might get something like this. CH3, CF2, CH2Cl. Any CFC, but it's got a Cl attached. Basically, that CCl bond can break, and you can have any CFC you like here. Those bonds don't break, but what we'll do, that will separate that into two free radicals, like that. So you get your chlorine free radical through a CFC breaking. I'll try and show you another one in a bit more detail. Right, you've got to have C's. CF bonds don't really break, they're too strong. So that there, I suppose, you can have any one of these, but that's the key. That's CCl. Breaks. UV breaks that to make what I've shown you above there. Okay. The chlorine free radical. The chlorine free radical. That's what causes the damage. Okay. Now, so any CFC, you should be able to show two free radicals in an initiation step being generated, one of which must be a chlorine free radical. The other free radical is basically what is left, but you need to show a chlorine free radical being produced. There you go. Right, next. Now you need to know this sequence, you need to learn this sequence. It's no big deal, just remember it, it's fine. So what happens? This is what you might call propagation. So it has echoes, propagation, of the homolytic free radical substitution reactions we looked at with the alkanes. Okay, very similar. You've got an initiation step to form the chlorine free radical. You've got a propagation step to destroy the ozone layer, because this is what happens. Now you must learn these. They might come up, they can come up everywhere. They can come up in A2, they can come up in AS, because they're a standalone. So propagation is this: chlorine free radical bangs into an ozone molecule, Okay, no good will come of it, because it turns the ozone molecule to an oxygen molecule, which you might think sounds okay, but we need the ozone. We don't want oxygen. Thank you very much. It messes with the equilibrium that we showed you earlier, and you end up so free radical plus molecule makes molecule plus a strange and weird intermediate free radical. There, learn that. Okay, now the intermediate free radical here, so this is the second propagation step, will bang into another ozone molecule to make 2O2. Looks complicated, and I'm afraid regenerating a chlorine free radical. The whole point of this is that the free radical is not being used up in these two collisions. The free radical is still actually there, so it can go on and cause much more damage. I don't know the figures, but they reckon that maybe one chlorine free radical can destroy I think 50,000, I'm guessing a bit, 50,000 ozone free radicals before it meets perhaps another free radical and terminates. So they go on and they bash, bash, bash and cause these holes in the ozone layer. So those are the two propagation steps that are involved, but we can play with those a bit. This is quite an interesting technique that you meet actually later on when we're doing things like what's it called, rates of reactions and developing reaction mechanisms. You can put these two equations together to create an overall, just the same as you would with anything else. If you put them together, overall, I quite like this, it's quite clever, just like any other sum. Chlorine free radical on the left, chlorine free radical on the right. Okay, so that can cancel. Weird intermediate free radical there on the right, weird free radical on the left. That can cancel. What does that leave us with? Leaves us with this overall equation for the destruction of chlorine free radicals. If you add those together, you end up with this. (2O3) makes 3, oh dear, I'm not concentrating, O2. 2O3 makes 3O2. That essentially summarises, without showing the intermediate free radical propagation steps, the destruction of the ozone layer by CFCs. That's what it does. Two ozone free radicals become, two ozone molecules become 3 oxygen free radicals. Catalysed that process by chlorine free radicals, as we can see, generated through the use of CFCs. Okay, so that question, essentially, if you look at the pack, you write down that information to answer the question in this Haloalkanes pack, which is here. Page 5 of 13, there it is. Okay. Now, okay, so that's covered that. I think that's covered free radical substitution and the ozone layer reasonably well. Anything else to say? The only other thing, looking at this pack as well, bear with me, I do apologise. Right, okay, so that's fine. Let's have a look at a few weird bits and bobs. The very first question in the pack might cause you some grief. So let's have a look at this. Still on Haloalkanes. Although this I'm going to show you now is a very general thing that covers AS, particularly A2 organic chemistry. And although we've not met nucleophilic substitution much, only in haloalkanes, you will see that this idea of nucleophilic attack is all over the A2 specification, all needs to be sorted out. All right, now I'll show you what I mean. Right, haloalkanes, good example. Here is a haloalkane, any one you like, it doesn't matter at all. Let's show the bonds that matters here. It's a bromo haloalkane, and that's where the action is. So I've sort of highlighted that bit of the molecule. Now we've already said, okay, I'll try and show you this as a sequence, that this is vulnerable to nucleophilic substitution, and the classic nucleophile produced from sodium hydroxide solution, I've shown you this, is the hydroxide nucleophile right there. Okay, that will come in, lone pair, it's got a negative charge on it, probably the most famous nucleophile of them all. Movement of a pair of electrons, movement of a pair of electrons. Arrow ending up with this. It's a one step. So it's easier than some of the mechanisms that have been done, such as alkenes, that type of thing. Okay. Bang, straight in, you've made an alcohol. And the bromide over here, lone pair on it now from the movement of that double-headed arrow there to form that. And that, if there's any silver around, you'll get cloudiness. So you can monitor how quick the reaction does. I've covered that in the previous one. But this idea of nucleophiles, you've got to just think outside the box. Yes, that's the one specifically mentioned, but you know what? You can have all sorts, as long as you, particularly with oxygen, as long as you're on oxygen with a lone pair in it, it can behave as a nucleophile. I'll give you the example straight from the pack, exactly from the pack. Same haloalkane, can be any, Br. What about this? O. Now, minus, instead of an H on it, that's a hydroxyl nucleophile. But we can have a hydroxide nucleophile, but we could have a methoxide nucleophile simply by replacing that H with something else. A methoxide nucleophile will be replacing the H with a methyl group. They exist. There's no need to worry about it. Okay, so that's methoxide, hydroxide, methoxide. Okay, it's not really in the spec, but you have to think outside the box. It doesn't matter what's joined there, doesn't make any difference, but you've got your potential for nucleophilic attack because there's a lone pair right there. Bang, bang. Should have put my delta plus, delta minus in there. Okay, what do you make? Doesn't matter what you make. You make what you expect to make. O, CH3. Just the same as the one above it, and you kick out bromine. What I'm asking you to do is be adaptable and flexible with the nucleophile, and at A2 I keep saying this, be adaptable, be flexible. So we'll do two more. So anything that's got a lone pair on it can behave, can attack nucleophilically, anything. So this one, okay, you can get all sorts of weird ones. Well, let's have a butoxide nucleophile. O, lone pair, minus there, C4H9. Okay, methoxide, butoxide. Who knows what the... It doesn't matter what you're making. This is outside of the AS spec. Okay, but you're going to shove that on. Kick the bromide out. Don't know what these are called, no idea, it's irrelevant. So there's your starting parent, but you know, these are the offspring that you've got to be able to cope with, and they're exactly the same. Okay? And let's have a totally weird one, right? Imagine you get this in the exam, right? I don't know. We'll do one more. We'll stick with bromo because then you've got at least some kind of pattern. Now what about this? Nucleophile like this. Let's have a wild one. It doesn't matter. O minus C. Double bond O. That is a carboxylate nucleophile. Probably derived from a carboxylic acid. Who cares? That's the bit that matters. That can attack nucleophilically to that carbon delta plus. That bond can break and you'll end up making this. Name that. What sort of compound have we made there? That one we know. That one's on the spec. This reaction is not specifically shown. Plus Br minus. It's not specifically shown. You don't, but you might be asked to say this is a nucleophile, blah 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 blah. It can react with a haloalkane. What is going to be made? Show the reaction. You should be able to do that. You don't have to remember all these. You just remember the parent and you apply different scenarios to that parent. It's as simple as that. Anything else to say? I don't think so. What's this substance here? You should know, as it turns out, we appear to have made. You should be able to tell me, right? It's an ester, isn't it? Propyl ethanoate. That's what it is. Normally you draw it around the other way, but you've got to be flexible about the way we draw these things. So that's a summary of what I would call AS, high level nucleophilic substitution. Okay? And it really is very much similar to the way we go at A2. We meet nucleophilic addition and substitution at A2, and you have to be able to react anything with anything and look for the key drivers of what's going to react with what, and then you can't really go far wrong. Thank you very much. I'll see you soon.